Hi class, this video is going to cover basically an outline of Unit 4 and then get more in depth in the materials of 5.1 and 5.2. So before we do that though, let me say a little bit about Unit 4. If you look at the syllabus, it seems like there's quite a bit going on. Yes and no. So we definitely have to cover the quantificational logic, second order logic. That is a requirement by the university. We will not cover it in as much depth as propositional logic. And then we'll do a couple of topics after. More generally, Unit 4 is going to check all the boxes, and then it's also going to be kind of gesturing at some other topics in logic in case you end up taking courses beyond the introductory in logic. And the exam will reflect that. Because we're not covering any of this in super depth, the exam will be a little more exploratory in nature and a little less rigorous. You will have to do a couple of proofs, of course, but nothing will be covered in as much depth as the previous two units. So be aware of that. And so what are we doing? Roughly speaking, we're doing the rest of logic. We're going to do what's called second order logic. And today we're going to cover 5.1 and 5.2, maybe even gesture a little at some of the stuff going on in 5.3 because it's neat. But the chapter 5 stuff is introducing this new apparatus in logic and showing the need for it, and then after that we'll move into working proofs in chapter 7. But more generally, think of this as building on to the system we already have. We're already pretty good at propositional logic from the previous couple of units. We already know the basics of translation, etc. So think of this as adding a layer of complexity rather than starting anything new. But Ulrich, Gustason start with a very obvious case of why we can't just leave it at propositional logic. If you watched some of the introductory videos, the optional ones, etc., there you see a classical argument, all men are mortal, Socrates is a man, therefore Socrates is mortal. Well, suppose you had to symbolize that with just propositional logic. Well, all men are mortal, Socrates is a man, therefore Socrates is mortal. What happened when we translated into propositional logic is we went from a clearly valid argument in terms of everyday language to a clearly invalid argument using propositional logic, first order logic. And so this alone should tell you we need something more. We need to instead introduce second order logic, that is logic that separates subjects and predicates. That's why it's also called predicate logic. And that's what we're doing. And in 5.1, we just work on translation. In 5.2, we work on basically relations and translation of relations, and the latter will be very important for working on validity and inferences in chapter 7. So that's what we're up to. So how do we start making these kind of distinctions? Again, the general rule is to separate subject and predicate. And to do that, we might have what are called singular terms. Singular terms are what they sound like. Terms that designate exactly one thing. So Mickey, at least in terms of this guy. But also things like the capital of Ohio. That's what's called a definite description. It describes exactly one thing. And so what we do with those is singular terms are translated as lowercase A through T. We save the end of the alphabet for reasons we'll talk about later. So, and then we also have general terms, such as is wise, is human, is awesome, likes tacos. These are all given to things like properties, etc. And those are translated as capital letters. And weirdly, the thing it'll take a little bit of getting used to is those go first. So if I wanted to say something like Socrates is wise, well, wise is the general term, so it's a capital letter. And then Socrates is the singular, and it would translate as something like that. Socrates is wise. And that's what's called a singular sentence. Just with a simple singular term and a predicate together, that's a singular sentence. Now, notice that these are simply true or false. These are kind of the building blocks in the sense that atomic statements were in previous units. And that's a singular sentence. However, if we left it at that, we still couldn't translate all men are mortal, Socrates is man, Socrates is mortal validly. Instead, and this is where we're going to really add to it, we need to introduce quantities. All, no, some, etc. And so this is what 5.1 really adds. But let me take it in two steps. Go back to the father of logic, Aristotle. Aristotle said all logic could be done using syllogisms, specifically categorical syllogisms, which use all, no, some. And there is a whole lot of logic that can be done with all, no, some, such as up here. All men are mortal, all persons identical to Socrates are men, all persons identical to Socrates are mortal is a simple way of translating that to simple all, no, some. So Aristotle is certainly on to something when he said that all logic can be done all, no, some. It's technically false, but you could do a whole lot of it. And so the general move is if we add this stuff, that is separating subjects and predicates, and add that to the quantities of all, no, some, we get a very, very, very rich logic that could cover this kind of stuff and all sorts of other stuff. So how do we get to this? We have to introduce quantifiers. And this is really what we're adding in Chapter 5. Everything else just builds off of this. Man, it's hard to talk right at the same time. Quantifiers. There are 2 quantifiers. You'll find the precise statements of them on 145. But generally, there's the existential quantifier. This translates roughly into the sum. That just says something exists. And so what does this look like? Big backwards capital E. And if you're having trouble finding that on the Blackboard discussion boards, it's perfectly fine to use just a capital E. So this is an example. If I use a concrete such as F, that's an existential quantifier that says there exists an X such that that X has F. So I don't know why I used F. Let's say from Frankfurt. This says there is someone from Frankfurt. that is different than saying Socrates is from Frankfurt, which would, of course, just be capital F, lowercase f, S. So that's the existential quantifier. By contrast, the universal quantifier doesn't have this backwards E thing, just has the parentheses X. So here's an example. For all X, HX basically says everyone has property X. So everybody is a human, maybe. Now, notice I'm fudging things a little here quite intentionally because these don't always quantify over everything in existence. Instead, we must talk about what's sometimes called a universe of discourse. So what things are we talking about? Ulrich Gustason give a good example of, well, if I'm in a classroom and I say, everyone is here, I very clearly mean everyone who's supposed to be here, that is registered for the class, etc. And so that's the universe of discourse. And that's fine because you could still make inferences off of it. So certainly from the fact that everyone is here, it follows that Mark is here. Because Mark is of the class, Mark is a member of the universe of discourse. And so if it's true that everyone in the universe of discourse is here, it's true that Mark is here. So those are the pretty quick notions of universal and existential quantifiers. But that's the general idea. Having said that, you never see statements that look like this. Instead, go back to Aristotle. So remember, Aristotle said that we could do a whole lot of logic using categorical statements, all know some. And so what we see and what we need to get used to are four types of statements in logic. They're called A, E, I, and O. A statements are always of the form all A or B. E statements are always of the form no A or B. I statements are always of the form some A or B. And O statements are always of the form some A are not B. Up until a few years ago, they always made us teach the Aristotelian categorical logic in this course. They don't anymore, which is sometimes good, sometimes bad. I will say that if you're going into pre-law, make very, very sure you get good at categorical syllogisms. Or I guess if you're going into philosophy, you probably should learn them as well. But for now, we only need to learn this because we can translate these four statements into quantifiers. So anything we could say with all know some, we could say using our quantifiers above. So at A statements, if I wanted to say all dogs are mammals, it certainly wouldn't be for all X, X is a dog and X is a mammal. That's crazy. That says everything in the universe is both a dog or a mammal. Instead, what all dogs are mammals is really saying is if it's a dog, then it's a mammal. And so every A statement will be translated like this. For all X, if X is a dog, then X is a mammal is exactly what we mean when we say all dogs are mammals. Certainly doesn't say all mammals are dogs, certainly doesn't say pens are dogs or anything like that. It just says if it's a dog, then it's a mammal too. So that's how we translate all A statements. Next we have the E statement. Well, no dogs or crocodiles is going to look like this. For all X, if X is a dog, then X is not a crocodile. So every E statement translates like this. Let's do the I statements. Some students are sophomores. Nope, that's bad. They both start with S. Some students are juniors. Well, we certainly don't want to use an if then. If they're a student, then they're a junior. That clearly doesn't follow. Instead, it's just saying there's some member of the class that is both a student, sorry, class in that sense, and a junior. So I statements translate like that, that there is some entity that is both a student and a junior. There exists such an X. And then very similarly, if we said some students are not juniors, then we would say there exists something such that it is a student and that it is not a junior. So every O statement translates like that. Okay, why am I going over these? Put the two pieces together. This is how we could do A, E, I, and O. Almost all logic can be done with A, E, I, and O, which means for translations, these are going to be your best friends when we're translating with predicate logic, that if you can figure out what it's saying in terms of A, E, I, and O, then you can translate as well. So for instance, if I say, nobody was late today, that's very clearly logically equivalent to no students were late, et cetera, et cetera. And so if we get in the habit of just translating everyday English to these kind of things, then we can translate pretty well into predicate logic. So make sure you're aware of these, and one of the exercises today is going to emphasize that. So that's the first thing I wanted to say about the translation. Second of all, notice I've been using X here, so we use individual variables. So the reason we save the end of the alphabet, W, X, Y, Z, are things that can change. So be aware of that notation. And the other thing I want to say when you're doing translation is about negations. So this is a little bit similar to, long before we learned the De Morgan rule, we realized we could translate neither as saying not one or the other, or we could say not the first and not the second. Very similarly, you have to, there's things we know as long as we draw it out and take it slowly in terms of predicate logic negations. There's a couple of things that are equivalent, but we have to be careful, because if you move the negations in universal terms, they say something different. For instance, if we did this, this says everything is non-J. Whereas if we did this, we say not everything is J, has property J. And so those are very, very, very different. So if I'm saying everything is non-J, what I'm really saying, it translates the same, is it does not exist anything that is J. Remember, this is the existential quantifier. By contrast, if I say not all, I'm actually saying some are not. So those are the equivalents with negation when you're translating. We'll learn those as formal inferences a little later in Chapter 7. But be aware on that. And again, it's like the neither thing. It's not that hard to remember if you realize what they are saying. So So I always read this as for all x, and I read this as there exists an x. So for all x, x does not have property j is the same as saying there does not exist an x that has property j. Here, it's not the case that all x have j means there exists something that does not have j. So there's that. I'll probably end this part of 5.1 with the translation of the original argument. All men are mortal. For all x, if x is a man, then x is mortal. Socrates is a man, therefore Socrates is mortal. There's the argument. Just by talking it through, we know it's valid, so we know we must be able to make some kind of inference with these quantifiers. That will be the topic of Chapter 7. I'm going to talk about 5.2 now. You're welcome to pause and reread 5.1, work on the exercises, etc. first if you'd like. But 5.2, there's a lot of important kind of technical derivations and things that go through there. And it does get a bit technical, I apologize, but it's about relations. And the reason it matters is we really want to pay attention to scope issues with bound and free and open sentences, because those are really going to matter to validity of inferences when we're allowed to draw an inference and when we're not. But having said that, if you set that aside, there are some senses in which it is straightforward. First of all, just when we're talking about relations, we just have two or more. So if you have two, it's called binary or didactic. This just says x bears this relation to y, whatever that relation is, and a relation can be a property, so we could certainly do it. So the order does matter. Think of relations like taller than. X is taller than y is true, then y is taller than x is going to be false. So the order matters, but once we start doing this kind of thing, the rest is actually a lot of what we've already talked about. So for all x and for all y, if x bears a relationship to y, then y bears it to x. So, by the way, this is actually just a definition of symmetry. This says a relationship is symmetric. So, but again, the more important part is how I read that. For all x and for all y, if x bears a relation r to y, then y bears relation r to x. So those types of relationships are called symmetric. Not all relationships are symmetric. So obviously taller than is not a symmetric relationship, but is as tall as is. If x is as tall as y, then y is as tall as x. So that's how we read these. You know what, just for the record, there's a couple of interesting relationships that I'll just mention on here. Another one is transitive, for all x and for all y and for all z. If it is the case that both x bears a relation to y and y bears the relation to z, then x bears the relation to z. So we talked about transitivity a while ago. So taller than is a transitive relation. If x is taller than y and y is taller than z, then x is taller than z. So not all relations are transitive, but that's, again, we're learning less about relationships here and more just about how to read these things. Then there's a third relationship that's kind of interesting called reflexive. What does that mean? A reflexive relationship bears the relationship to itself. So for all x, x bears the relationship to itself. That would be a reflexive relationship. So again, as tall as is reflexive. Everyone is as tall as themselves. Is identical to is a reflexive relationship, etc., etc. So that's just a little bit of how we read relationships. Otherwise, I think the discussion in Ulrich Gustason is pretty straightforward. But pay special attention to bound versus free. So the definitions are on 160, but a bound relationship, a bound variable happens if and only if it's either part of the quantifier or else lies within the scope of a quantifier containing the occurrence of the same variable. So for all x, if wx, then wz. As that an example, x is bound. By contrast, z is free. So a variable's free if and only if it is not bound. That is, it is not part of the quantifier, and it doesn't fall under the scope of this quantifier. And you say, wait a minute. It is the fact that it's in the parentheses there make it fall within the scope. It actually doesn't, for reasons they'll talk about a little bit. However, if by contrast I had this, then they'd both be bound. Again, it seems like a lot of nothing right now, but all the inferences you can make with quantifiers hinge on free and bound, so make very sure you read that carefully and that you can complete the exercises about which are free and which are bound, because it'll matter later. An open sentence, by the way, has at least one free variable. As such, open sentences can be neither true nor false. By contrast, any sentence that is true or false is bound. So notice, if I say all dogs are mammals, or if it's a dog, it's a mammal, X is bound. So even though this doesn't have any singular sentences, right, it's still in terms of general terms, it's true that all dogs are mammals, even if I don't bring, spot into it. And so that's another way to kind of double check to make sure things are right, is if it's the kind of thing that is true or false, then it has all bound variables. If it's the kind of thing that can't really be determined as true or false, then there's a free variable in it. So we're getting a little long here, but I do want to add just a little bit more in terms of practice. If you look at the ones on 163, these are how we kind of start mixing in what we know. There's the statements 9 through 14. Al struck something. Well, that's the kind of thing that could be true or false, which means we should be able to symbolize it somehow. But how do we go about doing that? Well, Al is something concrete. And so we should be translating Al rightly as a singular term. So Al is a lowercase a. But Al struck something. Well, something should be translatable as an I statement. There is something that Al struck. And so we start thinking about the existential quantifier. There exists a thing such that Al struck that thing. So that's how we do the very kind of basics of relationships combining singular and general terms, and making sure that we have bound variables. Let's do just one more. Well, let's do a couple more. So the next example is something struck Al. Well, there is a thing such that it struck Al. Again, order matters if the relationship is not symmetric. Then number 11 says nothing appeals to Bill. Nothing means no. So we're using a universal. So the capital A is appeals. If we said this, we would actually say, for all X, X appeals to Bill. This is a way of saying everything appeals to Bill. Instead, for all X, it is not the case that it appeals to Bill. That's how you read that, and that is exactly what the sentence said. So that's a good kind of warm-up. Otherwise, I want to turn you loose on your own, and we'll talk about the stuff more in the recitation. But that's the very, very brief gesture at 5.1 and 5.2. Again, you want to read all of this in terms of, yeah, you're going to have a translation section on the final, but the more important part is making very sure that you can eventually use the inferences in Chapter 7, which will require some of what we talked about here. And so we'll be talking about Chapter 7 in the next video. Otherwise, I turn you loose to practice, practice, practice.